Hello, welcome to this week's Naked Scientist with me, Chris Smith, and with Dominic Ford.
Hello, and this week, scientists see people's dreams, the next generation of batteries for electric cars, and is a gut bacterial transplant the future for weight loss treatments?
Plus, we hear from Perth-based astronomer Kirsten Gottschalk as she heads deep into the Australian outback to take a look at the next generation of radio telescopes.
If you'd like to get in touch with us here at The Naked Scientists, email chris@thenakedscientist.com, tweet @nakedscientists, or find us on Facebook.
The Naked Scientists podcast is powered by ukfast.co.uk.
And joining Dominic and me to take a look at what's making science headlines this week are Phil Broadwith from Chemistry World magazine, Laurie Winklis from the National Physical Laboratory, and neuroscientist David Weston. He's from Cambridge University. And Dominic, scientists can now physically see what people are dreaming about, they're saying.
That's right. What people see in their dreams can be decoded with a brain scan. Now, this is a team led by Tomoyasu Horikawa of the ATR Computational Neuroscience Laboratory in Kyoto, Japan, who worked with 3 volunteers who were invited to try to sleep while lying in a functional MRI scanner. It's quite a noisy environment, so they gave these volunteers headphones, and I think they played them some music to try and help them to relax. But these volunteers must have had a lot of patience because they were asked to repeatedly drift off to sleep. And then they were woken up after about 6 minutes and asked, what were you dreaming about?
Yes, because they were looking at the brainwaves to see when they nodded off and then immediately plucked them from sleep and said, did you see anything?
So that's right. This MRI scanner was making maps of where the brains inside these subjects were active. And they then compared these maps of brain activity with what these subjects reported when they were woken up. And they then ran this through a computational code to look for patterns between what people were experiencing in their dreams and what areas of their brains were active.
So if the person who's just been woken up says, I dreamt I was coming out of a building and got into my car, they'd say, well, the dream was about buildings and cars then. And so they'd be then assigning that pattern of brain activity they'd seen in that person to, it must be something to do with cars and buildings.
That's right, and the way that they tried to associate whether there were similarities between visual experiences and wakefulness and in dreaming was to then go off on the internet and try and find images of these objects that people said they were dreaming about, show them those images while they were awake, and to see what the brain patterns were then, and see whether there were similarities between the brain patterns when people are awake and they see a car and when they experience a car when they're dreaming. And what they found was there were actually quite a lot of similarities in the visual cortex.
So basically that confirms the claim that when we nod off to sleep and the same brain areas that are active during the day get active when we're dreaming, that is the basis, the neurological basis of the dream, main point 1. But point 2, they can actually now interpret that brain activity and say, well, if the brain is showing a certain pattern of activity, that means the person must be dreaming about cars or ships or a walk in the countryside because, you know, we've seen them show that pattern of activity and they've reported that's what they were seeing when they had that brain activity previously.
That's right. There are 2 angles of this. There's the angle of understanding where the dream is originating in the brain and what's happening when we're dreaming, but also it's about understanding what's happening through the night when we're dreaming, because most dreams aren't recalled in the morning. We forget them. And this means that you can scan people non-invasively, potentially, throughout the whole night and see what they're dreaming when.
David?
Did the scientists try to reverse engineer this, so record the brain activity and then try to guess what the people were dreaming about? Or is that a little bit too advanced for their kind of technique?
So what they've been doing so far is just taking accounts of what people were dreaming about and then comparing that with the brain activity they saw. I think in the future they would very much like to be able to non-invasively guess what people are dreaming about, but they haven't done that work yet.
It's quite a scary prospect, though, isn't it? The fact that, you know, if a brain scanner learns your dreams, then you could put someone in there for the whole night and find out basically what they dreamed about all night.
Eavesdrop on their thoughts.
Indeed. Well, one big dream is to try to come up with batteries that don't cost a fortune but do make electric cars a viable possibility, and that's become a step closer this week, Laurie.
Yes, absolutely. There's a group in Germany in the Fraunhofer Institute in Dresden, and they've actually used the same kind of architecture as a standard lithium-ion battery that is normally used in an electric vehicle. And they've done a little bit of new engineering, which has improved both the power of the battery and has reduced the cost. So it sounds a bit like the Holy Grail. What they've done is actually relatively simple. They've replaced the expensive elements in a lithium-ion battery, which is normally cobalt, which is used in one of the electrodes of the battery, and they've replaced that with sulfur, elemental sulfur. And by doing that, they've massively decreased the price of the battery.
How does it work compared with a lithium cell? Is it otherwise exactly the same? It's just using these two alternative chemicals means that they're just much cheaper?
Well, the major problem with these lithium-ion batteries is the kind of range and lifetime. So most lithium batteries in a car have to be recharged after just 100 kilometres of driving. So they're not really for long journeys. So what this research has shown is that by changing the combination of chemicals inside the battery, they can actually reduce the problems of short circuiting, which is kind of what defines the lifetime of these lithium-ion batteries normally. What ends up happening is that some of the material in the electrodes actually creeps into the electrolytes and can spread across the whole size of the battery and cause a short circuit. But by changing the elements, they've reduced how quickly that short circuit can happen. And in terms of comparison with how the lithium-ion batteries operate now, they actually have a higher energy density. These lithium-sulfur batteries have an energy density of about 500 watt-hours per kilogram, which is twice as much as the lithium-ion batteries that are currently being used in our cars. And what that means is that for the same weight of battery material, you could actually drive double the distance.
Phil?
So, Laurie, why haven't we thought about this before? I mean, the problem of sulphur leaking into the batteries has been around for quite a while. So what's different about what these guys are doing?
Yeah, it's a very good point, actually. These batteries have been known about for a long time, but the only extra bit that they've brought in is a layer of porous carbon, which they have surrounded the elemental sulfur electrode with. And what that does is that the pores are so sized that they trap the sulfur inside the carbon. So eventually the sulfur will leach into the electrolyte, but it will do so at a much slower rate. So by doing that, they've increased the lifetime of standard lithium sulfur batteries that, as you said, have been around for a while.
How long before this is actually scalable and deployable into the market rather than just being an experimental tool, Laurie?
Well, at the moment, these scientists are exploring all possible large-scale manufacturing methods for these. They've produced quite a large number of prototypes, though, and everything is starting to move towards patenting. So I don't think it's going to be very long, maybe just in the next 5 years.
There's certainly a big demand, isn't there?
Absolutely.
Now, Phil, I think you've got a story all about X-ray crystallography.
Yes, we're talking about Japanese scientists who found a way of doing X-ray crystallography, but without any crystals, which sounds like a bit of a kind of funny thing. But basically what they do is take a molecular sponge, a metal organic framework, and absorb the molecules into that, which means that they order themselves in a kind of regular array and don't need to actually pack into a proper crystal.
Of course, X-ray crystallography is big business. I mean, this is the technique that led Watson and Crick to the structure for DNA, for example. Yes,
and Dorothy Hodgkin for penicillin and vitamin B12, and numerous Nobel Prizes in chemistry for protein crystallography.
So it's a very powerful technique.
Yeah, absolutely, as long as you can crystallise the stuff you want to look at.
And that's been the major stumbling block, hasn't it? Because we just couldn't get crystals of some of the important things we wanted to look at.
Yeah, I mean, particularly a lot of organic molecules. I mean, proteins are a massive example. I mean, this technique isn't quite up to doing proteins yet. They're a bit too big. But small organic molecules, like the ones that you might isolate from plants or from things in the sea where you might be looking for new drugs and things, often are liquids or oils, and they simply won't pack into a crystal because they have long, floppy organic molecules. So if you could absorb them into this molecular organic metal organic framework and get some crystal data, you can actually see the arrangement of the atoms, and you can get information that you just can't get spectroscopically other ways.
What have they looked at so far using this?
Well, they started off with quite simple things like cyclohexanone, which is very, very simple. But they moved up then to a molecule called miacosine A, which is a really long chain of 30 carbon atoms, but it has some bits and bobs hanging off the side, which it's really important to know which orientation they're sticking in. This is a chiral molecule, so it has left-handed and right-handed forms, and you can tell the difference between those by looking at the crystal data.
David?
So one of the kind of limitations of crystallography in terms of using real crystals is resolution. So what some people are quite worried about is that if you've got a crystal that's relatively poor quality, you're going to get a very poor crystal structure at the end. So how does it work with this framework? What sort of resolutions can we resolve to?
Okay, well, I'm not sure about the absolute resolution, but the researchers do say that the quality of the data is not quite up to the same as you would get from a proper crystal, but it's better than nothing. If you can't physically crystallize the stuff any other way, then this is better than nothing. It also doesn't use very much material, which is the other benefit. They've been able to get these kind of structures with less than 0.1 of a microgram of material, which again is very useful for things like natural products. If you're having to extract several tons of jellyfish, for example, like the guy
thoughts.
to get a few micrograms of stuff, then the more data you can get with that tiny amount of material, the better.
And scientists therefore might be able to sleep a bit easier. And that's a horrible link to David. You've got this item, very intriguing, on a better way to send people off to sleep if they've got insomnia.
Yes, so this is a new drug that's believed to be able to overcome insomnia, and particularly without the horrible hangover that you sometimes get from these sleeping cures. And it's currently being tested in the US now. So this is a paper that's been published in Science Translational Medicine this week, and it outlines a new drug called DORA-22, which promises a good night's sleep without all of the side effects.
Sounds like you've already written the marketing speak for them. How does it work?
Well, if they're employing... So what they basically did was the lead author, Jason Uslaner, and his team characterised this drug, DORA-22, and compared it with a couple of different drugs that are already available on the market. And previous studies have shown that with typical hypnotic drugs, you get a range of cognitive side effects, and these can range from reduced attention or even lack of memory performance and things. So what they did in this battery of tests was to test the attention and memory performance of monkeys and rats. And they found that with the traditional hypnotic drugs, you get these deficits that have been associated with side effects in humans.
Sort of hangover the next day when you can't think straight because you're still sleepy from the drug that you took to deal with the insomnia.
Yeah, it's kind of characterised as cognitive impairment. So what they found with this new drug, however, DORA-22, is that you don't get any of these hangover effects, and that you can use it at a very low dose, which means that you don't get all of these non-specific effects, which is really a big plus for pharmaceutical companies because you want to reduce the amount of side effects.
What does it target in the brain? How does it actually work, this DORA-22 molecule?
So what's so special about this DORA-22 is that it targets a specific type of receptor located in a very specific part of the brain. So it targets something called orexin receptors, which are expressed in only about 70,000 neurons in the lateral hypothalamus in the brain. And compared to these typical hypnotic drugs, which target up to 20 billion neurons in the brain, we're getting a much, much more specific receptor activation here, or rather an antagonism in this case, which causes this effect.
And these orexin nerve cells, they're linked to wakefulness normally, are they?
Yeah, so when you activate these receptors in a normal situation, it promotes arousal, so people feeling awake. So the idea behind this study was to look at these receptors and say, OK, let's design a drug that antagonises it, so stops it from working. And that's what they've done with this DORA-22.
Now, David, I'm noticing we've had a couple of neuroscience stories this week, and it seems to be a theme because last Tuesday, President Obama announced the Brain Initiative, which offers $100 million of federal funding to map in detail the working of individual parts of the human brain. And this will obviously provide vital clues in treating diseases like Parkinson's and Alzheimer's. Why do you think this wave of funding is coming now for these kinds of conditions?
Well, it's kind of a prescient topic at the moment, the idea of the ageing population. So the increase in awareness for diseases like Alzheimer's and Parkinson's disease seems to be almost omnipresent. We've got this idea that we need to plough a lot of resources into neuroscience funding so that we can find appropriate treatments for these drugs.
Do you think $100 million? I mean, that's about, what, £60 million? Is that really very much? I mean, you look, the Human Genome Project costs $2.5 billion. And the Wellcome Trust in the UK, a major funding charity, gives away £650 million a year. Neuroscience is a big chunk of that, admittedly, but $100 million does not sound like very much to do what they're trying to say they want to do.
No, it's not a phenomenal amount of money. And if you look at the original application for this project, it was originally a proposal that was $3 billion that's obviously been scaled back to a $100 million proposal. So in the modern situation, research and technology is so expensive, and consumables that you use in the laboratory are so expensive that money doesn't necessarily translate into lots and lots of new drugs for us to use.
Yes, but it is extra money coming in from a source that wasn't there before. So I guess you could say something's better than nothing. And I guess you've got to kind of weigh up, comparing to, say, the Human Genome Project, how much new hardware is needed. Can we do a lot of these things with existing techniques so we don't need to necessarily invent new technology?
And I think the idea of raising awareness of neuroscience research is also a really key point here. And I think if we can galvanise the youths of today to then enter neuroscience research and feel that this is something that people find is very important, that that's only going to have a net positive effect.
The one thing I'm still concerned about, though, is the sustainability of this, because shoveling in 100 million, it sounds great, and it's led to a lot of headlines, which is, I'm sure, partly what they wanted to do, to inject some feel-good factor into US and an international, global research. But at the same time, that's not very much money to do what they're aspiring to do, and it's one thing to start it, it's another to keep these things sustained, isn't it?
Yeah, I mean, neuroscience research, like many other areas of research, requires dedication over long periods of time. Sometimes these technologies take decades to go from a kind of preconception to the final product. So we really need to be looking at this over a much longer term.
David Weston, thank you very much. And thank you also to Phil Broadwith from Chemistry World and Laurie Winklis from the National Physical Laboratory. You can find out more information, including the references to the papers that we've discussed, on our website at thenakedscientist.com/news.
This is The Naked Scientist with me, Dominic Ford, and Chris Smith.
Gastric bypass surgery, which reduces the capacity of the stomach, is now a regular weight loss option. But new research suggests that changes to gut bacteria which follow the surgery can be as effective as changing the stomach capacity itself.
We're joined by Dr. Lee Kaplan of the Massachusetts General Hospital to find out more.
Lee, what's actually involved in doing what we put in inverted commas and dub a gastric bypass operation?
Well, you divide the stomach, meaning you cut the stomach so that there's a small pouch made out of the top part of the stomach, and that's separated from the rest of the stomach. And then you cut the bowel distally further down, and you bring it up so that you're emptying that little pouch, that little stomach pouch, directly into the small bowel. So the food flows through the esophagus, the swallowing tube, into the small gastric pouch, and directly into the middle part of the small bowel, bypassing the rest of the stomach, the first part of the small bowel. And in doing so, it was always thought that what you were doing was preventing people either from eating or absorbing what they ate. And now we know that actually that's not the case.
So critically, the stomach, the residuum of the stomach is left there in situ, and the part of the small bowel, the duodenum that the stomach connected to is still there. It's just that food is bypassing those two anatomical structures and going straight into a part of the small bowel a bit downstream of there.
Exactly, and those portions are not seeing food anymore, they seem to be very actively involved in the effect of the bypass. If you simply cut out the stomach, you wouldn't see as much of an effect as you do when you separate the stomach and leave both parts intact, or both parts in the body. So the part that's not seeing food is now sending some kind of a signal to the rest of the body. You know what? I think we need to sort of change the balance of energy here.
And when people undergo this procedure, roughly how much weight can they lose?
Well, the average is you lose about 2/3 of the excess weight, the weight above what normal would be. And there's quite a bit of variation. Some people lose only half that much weight. Some people lose more than that much weight. But on average, it's a highly effective intervention, much more effective than anything else we've got so far.
So what was your hypothesis when you came at this study?
Well, some years ago, workers in Jeff Gordon's laboratory in St. Louis, Missouri, had found that the microbiota correlates with whether an animal has, or a human being has, obesity or is thin. And further, they showed that if you take the microbiota, the bacteria that live in our bowels, and you from an animal that is fat, and you give it to an animal that doesn't have a microbiota, that was a sterile animal that was grown special, that animal will gain more weight than if you do the same kind of transfer from an animal that was lean. So we knew from those experiments that the microbiota was involved in some way in regulating energy balance, body weight, body fat, metabolic function. So we asked the question, could the gastric bypass be working by changing the total population of bacteria that are in the microbiota? That was the premise, and of course the answer was yes, we could.
So how did you actually do that?
First, we asked the question of how does the microbiota change in response to the bypass? And are those changes really from the bypass, or are they from the weight loss that the bypass causes? And what we found was that there's a difference in the microbiota between thin animals and fat animals, sort of a difference in the balance of different types of bacteria, but that after a gastric bypass, you actually change it even more so that you get to a third type, or a specialized gastric bypass type of microbiota. And that change occurs with a gastric bypass, but does not occur when you lose weight by dieting the animals. So that's specific to a bypass. We then took the microbiota from an animal that had gotten a bypass, these changed microbiota, and we put it into another one of these sterile groups, animals with a sterile gut. And we found that when we did that, those animals lost weight. And again, that effect was specific to the microbiota after gastric bypass, because when we did the exact same transfer from an animal that became thin because we put it on a diet, it did not have the same effect in the recipient animal. So there's something about the microbiota from a bypassed animal that is able to cause a non-bypassed animal to lose weight.
Do you know what's actually going on as a consequence of the operation to trigger that change in the bacterial population that then has these onward effects?
Well, that's a great question, and we don't really know the answer. We have hypotheses that the changes in the structure of the gut cause a whole variety of signaling changes. We think that bile acids, which are secreted into the lumen of the gut, play a role. We think that the mucus layer of the gut, the mucus lines the wall of the bowel, plays a role. Just because of the nature of the changes in the bacteria, some of those bacteria that are favored after bypass preferentially get their energy from that mucus layer. But we don't really know the answer to that. One thing that's important to note, however, is that the biggest changes that we saw in the microbiota were in the bottom end of the bowel, in the ileum and in the colon, which is far removed from where the surgery was. So, of course, if you only had changes in the microbiota right where you operated, you might imagine it was some kind of a technical fluke. But here we're seeing that throughout the bowel, and actually in many other parts of the body, the microbiota fundamentally changed. So this looks like a systemic effect, but we don't yet understand why.
The obvious aspiration is to be able to produce that effect without having to do that fairly dramatic and in many cases life-threatening surgery.
Exactly. I'm not a surgeon, but I do take care of many patients who get the surgery. It can be life-threatening, although I have to say that it's a valuable intervention when used in the appropriate patient. And in the United States, at least, and it's actually less in the UK, but in the United States, only 1 in 400 patients with obesity get a gastric bypass. So rather than thinking about substituting something else for a gastric bypass, I'm much more interested in focusing on those 399 that are not receiving any effective therapy. So if we could harness the sort of the magic sauce of a gastric bypass without the bypass, we could perhaps apply it to some of those 399.
Lee, thank you very much. That's Dr. Lee Kaplan from Massachusetts General Hospital.
Now, how much do the oceans weigh? To find out, Planet Earth's Sue Nelson met Chris Hughes from the National Oceanography Centre in Liverpool to find out why anyone would want to weigh the oceans in the first place.
We know that sea level's rising. It's been rising at about 3 millimetres per year for the last 20 years or so. And we're pretty certain it's going to continue rising. But there are lots of different estimates of how much. So over the 21st century, it might rise by half a metre, or maybe even more. Whether it rises by a lot really depends on how much ice melts. The main source of water is the ice that's locked up in Greenland or in Antarctica, which can melt and fill the ocean. But the other way it can rise is you don't add water, it's just the water that's already there expands to take up more space because it's warming up. So we want to be able to separate out the two different sources of sea level rise. And in order to do that, we need to measure the mass of the ocean separately from its volume. The mass tells us how much ice is melting or even water pouring off the continents, whereas the volume tells us about the density change as well. So we need to separate the two out to understand what's happening.
So is this why you want to actually build an instrument, a device, that would, in the conventional sense of the word, quite literally weigh the ocean by going on the seabed, on the seafloor?
Yes, that's right. It came as quite a surprise to find that this might even be possible. When you look at the sea level problem, altimetry has been brilliant because it's measured the entire ocean. So the satellite measures almost the whole world. And we know, because we're measuring everywhere, that we're measuring the global picture. If you don't measure the global picture, you don't get the total. The ocean sloshes around in a very complicated way. And if you just measured at one place, you wouldn't see global sea level rise. You'd actually see mostly the sloshing or the local effects. So you need to do that global average. But it turns out, when we look at what ocean models can tell us, that when you look at the bottom of the ocean, things get much quieter. And especially in the tropics, there's so little of this sloshing going on long time scales. But it gets so quiet that if you just measure the pressure, you're not measuring the sloshing anymore. You are just measuring the slow rise of the ocean as the ice melts.
If you're measuring the pressure down, the force down on an instrument on the sea floor, how will that, though, make a global average? You're going to get a different measurement on the other side of the world.
Again, that's the surprising aspect of it. I think of it as a bit like when you're filling the bath. If you turn the taps on and look near where the taps are, you can't actually tell whether the bath is filling because there's so much splashing around going on. But if you look a long way away, all the ripples have damped out, and there's just a gradual creep of the level up the side of the bath. And that's what we're doing here. We're finding a place where all that splashing around isn't really influencing what we see. So all that's left is the global average.
Right then, let's get to the nitty-gritty. What will this instrument consist of, and how are you going to build it?
Well, that's the challenge. The same technology has been used for about the last 40 years, which consists of a quartz crystal, and the resonance of that crystal, the resonant frequency, depends on the pressure. But these have a problem. They have got much better over the years, but even so, when you put them down in 5 kilometres of water, they are still slowly crushed by the pressure. So we can't measure these changes in pressure on the very long timescales we would like to. It's not super difficult. We're talking about 1 in 10 million accuracy. So you want to be in 5 kilometres of water, measuring a pressure change equivalent to about 0.5 millimetre. That would be the level we would aim for.
How deep are we talking about that you're going? It's several thousand metres, I would imagine.
Yes, typically it will be sort of 3 to 5 kilometres. You want to be away from the edges of the ocean, so somewhere in the middle, and that's the usual depth.
So if you can't use these quartz crystals, what else are you going to use?
That's where we're asking for ideas. And one possibility is using something to do with electromagnetism, with light. So maybe we can do something to do with the refractive index of a fluid, which will change according to its pressure. Maybe there's something to do with the speed of sound that we could measure. Or ideas have been floated about using something which changes phase.
It is a sort of science and engineering challenge as well.
Yes, that's what we're trying to do. We want to get engineers around the world who've just not thought of this as a problem to bring their expertise to bear and come up with innovative solutions. It's a really fundamental piece of physics. Pressure is not a complicated variable. I'm sure there's someone out there who has a brilliant idea that would solve our problem.
Professor Chris Hughes from the National Oceanography Centre in Liverpool, and you can find out more on our website at nakedscientist.com/Planet Earth. This is For Naked Scientist with Chris Smith and me, Dominic Ford. If you would like to get in touch with any questions or comments, email chris@thenakedscientist.com, tweet @NakedScientists, or find us on Facebook.
The Square Kilometre Array is soon to be the world's largest and most sensitive radio telescope. Located in a remote part of the Australian outback, about 800 kilometres north of Perth, 2 precursor instruments, the Murchison Radio Astronomy Observatory and the Australian Square Kilometre Array Pathfinder, have already been built on the site. Kirsten Gottschalk from the International Centre for Radio Astronomy Research set out on an expedition to see the site from Perth with some of the engineers who work there.
We're just packing up the vehicle now, ready to head out on our trip. We've got about 8 or 8.5 hours in the car today up to the Murchison Radio Astronomy Observatory. Our destination for this evening is Bullardy Station, where we'll be staying, and then we'll get to head out to the MRO tomorrow morning. But at the moment, our first stop is going to be Bindoon Bakery for some breakfast. We've got about 600 kilometres of tarmac ahead of us and then another 200 of red dirt road.
The Square Kilometre Array, or SKA for short, is an international project which will be split between Southern Africa and Australia. Centred around the Karoo Desert in South Africa, an array of radio dishes will be built, which will stretch over distances of thousands of kilometres into neighbouring countries. In Australia, meanwhile, the Murchison site will be at the centre of a second array of radio antennas, also spread over distances of thousands of kilometres, which will utilise a new kind of radio receiver called aperture arrays. It's only in these remote and mostly uninhabited locations that radio astronomers can get away from the noise of mobile phones, Wi-Fi networks and television masts to be able to detect the faint radio signals that they're looking for. Together, the SKA's two arrays will form an instrument which will be around 10,000 times more sensitive than the current generation of radio telescopes, and will allow images to be taken of the faintest and most distant galaxies ever observed. By looking at distant objects, whose light has taken billions of years to cross the universe to reach us, it will be able to look back in time. The astronomers building the telescope hope that it will be able to look back so far in time that it will be able to see the first galaxies forming out of the smooth structureless sea of gas that was produced by the Big Bang.
It's now about 2 p.m. and we're still on the road. We just left Morawa, where we had lunch by the side of the road. We're now driving along a very straight road with some beautiful, beautiful blue skies ahead of us with some little wispy clouds around. It's about 30 degrees. As we head more north, we're getting progressively warmer. The fields around us are nice and brown and dry, and we're about to be passed by a road train with some ore. And the road is actually only single lane tarmac, so you have to go out onto the dirt to get past, and then all the dust comes in. That's not as pleasant as it could be. A 3-carriage road train just passed us, and now another one's coming back in the other direction that has 4 carriages. These trucks are huge.
The SKA won't just be looking at very distant objects. Within our own Milky Way galaxy, it will expect to discover thousands of pulsars, the fast-rotating remnants of dead stars, which emit beams of radio radiation from their magnetic poles and appear as radio sources which pulse on and off on each revolution, often hundreds of times a second. If 2 of these objects can be found in close orbit around one another, the way in which they move in each other's intense gravitational field will allow the SKA to put Einstein's theory of general relativity to the test.
So we just turned onto the road into the Murchison Radio Astronomy Observatory. We're driving along and we're going to get a glimpse of a telescope soon, I think, in the distance. I think as we round this corner we might be able to see a dish.
Dish?
Oh, we see one.
Where?
Up there on the left. It looks tiny from a distance, doesn't it? So we've just pulled up to the gate. We're going to say hello to Martin, one of the MWA astronomers and engineers who's opening the gate for us. Thanks, Martin.
Thank you.
And we're going to pull through, talk to Brian.
You guys saw the bung arrow on the drive-in, but there's another one just a couple of 100 metres ahead near that dip on the right-hand side.
Alright, we're being told to watch out for a bungara up on the right. We'll meet you at the Murchison Widefield Array.
Though construction of the SKA is still 3 years away, the Murchison Radio Astronomy Observatory is already home to 2 precursor telescopes. Australia's National Science Agency, CSIRO, is building the Australian SKA Pathfinder, ASCAP for short, on the site. When it is completed, this will be an array of 36 radio dishes, each of which measures 12 metres across. Nearby, the Murchison Wide Field Array, or MWA, is a much less conspicuous instrument. Rather than using dishes to reflect radio waves and focus them onto a receiver, it consists of tiny antennas, each measuring no more than a couple of feet across, which are arranged in groups of 16 called tiles.
Well, we've arrived on site. We've put our lunch in the fridge, and it's about 9:30, and I'd say it's already 30 degrees. It's getting really warm out here. And in our long pants and our long sleeve shirts and our boots for safety, we're getting a bit warm. But it's about time that we headed over to the Australian SKA Pathfinder to meet CSIRO over there, and they're going to show us around their new control building and the beautiful 36 white dishes that are popping up everywhere over there. So we'll head on over and we'll see what we can find out. So we've just turned back onto the road that goes straight down the middle of the MRO. We've got a breakaway to our right. Again, the MWA site is to our right, and to our left is ASCAP. Well, we can't see any of it yet, but as we come up here and turn a bend, we should get a glimpse of the ASCAP core, where there are about 11-12 of the 36 ASCAP dishes in a close area. They really do look small from a distance. It's not until you get closer you realise just how big they are.
Once you realise that the whole dish is actually sitting above the tree line as well.
Yeah, absolutely amazing country out here. It's flat as a pancake apart from the breakaways. There's, little bushes everywhere and a few trees that are maybe person height, but most of it is just flat red dirt, which of course makes it absolutely perfect for radio astronomy. One of the great things about radio astronomy in this region is that it is fairly low impact compared to other activities that happen in Western Australia, like other commercial activities. So with the Murchison Wide Field Array, we have mesh on the ground, then we have the dipoles clipped to the mesh. And if you needed to take that telescope away, the ground would be relatively undisturbed and you could rehabilitate it quite effectively. Same goes for ASCAP. You've got the central region where the roads are and where the dishes are built, but the rest of the landscape is untouched. So they're all pointing straight up at the moment, standing like sentries on the side of the road. We're now in the core region, so we're surrounded by ASCAP dishes in every direction. We're now wandering around the core of ASCAP, and this place is incredible. These dishes are massive, and we were lucky enough that one of the CSIRO workers just let us inside one to have a look inside, and there's so many cables and fibres and digital chips. It's such an interesting contrast to the fact that we're 8 hours from anywhere, pretty much. We're in the middle of a desert, in the middle of nowhere, which of course is where we need to be doing this radio astronomy. I'm looking up at one of the ASCAP dishes now, and this big, bright green checkerboard circle above the dish, and that is what we call the phased array feed. It's the brand new technology that CSIRO have invented, and they are just absolutely incredible. We've just been told they have 188 different feeds, so that means there's 188 different signals coming down off these dishes, allowing it to look at a broad section of sky. So usually radio telescopes only have one or maybe a few of these things, but these dishes have 188 of them. And hopefully it'll feed into the square kilometre array and be on the square kilometre array dishes. But at the moment they're building them for ASCAP. Another really, really interesting thing about these dishes is that they don't just move up and down and left and right. They also spin around completely, which sounds kind of trivial when you're thinking about it, but then you've got to think that there are hundreds of cables coming out of the top of this dish, and then you have to spin it around 360 degrees. So there's so much complex cable management inside these things. In fact, you go in and it's all just big racks of computing that takes in the analog signal and then more computers that turn it into a digital signal, and hundreds of cables being managed so that they can twist round and not get tangled or stop the dish from turning where it needs to turn. And now we are so lucky, they are just tilting the dish towards me. It's 12 metre wide bowl, basically, with 4 arms coming off it that lead up to the phased array feed, the green checkerboard, with all the cables coming down off it. It's actually quite funny watching someone use a remote control to tilt a telescope towards you.
We'll be hearing more from Kirsten's trip to the MRO later in the show. But first, we've seen that both of the precursor telescopes are pioneering new receivers to detect astronomical radio waves. Earlier, Ben Valsler spoke to a PhD student called Sarah Thompson from the Cavendish Laboratory at Cambridge University about her research into the physics of receivers to see how detectors like those used on the MRO can be made as sensitive as possible.
My research is focused on a thing called kinetic inductance detectors. These are superconducting detectors that would be used for cosmological or astrophysics observations from the ground or also in space. They're a bit like cameras, but they're not really used for visible light, they're more used for other wavelengths. What I actually research on is we make these devices and we test them in the lab to see how they behave as you change certain elements of their environment. And the idea is that we'll get a better understanding of the physics of these devices, and then you can make better devices.
So rather than building a new telescope,
Yep.
Your research will enable us to build better telescopes in the future.
Exactly, yes.
I know that I can pick up radio waves very easily using a bit of old coat hanger that's stuck in my radio. So what is a superconducting material, and why do we need these materials with interesting properties?
A superconducting material is simply a material which has a temperature at which there is a sudden change in the material. So above this temperature, it acts as a conductor or even sometimes an insulator. But below that temperature, the properties of the material change so that suddenly electricity flows through it with zero resistance. Basically, in terms of building a device or a detector, you instantly get a lot less noise in the device. Superconducting detectors tend to be a lot more sensitive than non-superconducting detectors. And in a world in astrophysics where we want to be able to detect more and more distant galaxies and stars, and with things like the cosmic microwave background radiation, which is very old and has been travelling since the beginning of the universe, there's not much of that light coming to Earth. So you're only talking about a very small amount of light, and you need to have a very sensitive device to be able to pick up that light and give you an accurate image.
With optical telescopes, of course, the way that we've done that is to get bigger mirrors, bigger lenses, larger areas to collect more light. Is there the same in microwave and in radio waves? Or are we just getting bigger?
Yes. If you're talking about the total amount of light collected, then a larger array will collect more light. But if you're talking about an individual pixel, that's one single detector. And if you want to be able to capture a single photon on that single pixel, then you need to make sure that a single photon will trigger a significant enough response from the detector that the signal will stand out clearly from the noise, the background of the detector. So you need, not only do you need a large array to capture more total light, you need more sensitive detectors to be able to actually detect that light when it hits the array.
So we are talking about detecting radiation from the birth of the universe.
Yes.
To me, I think that would need a very large bit of kit. But you've brought a few things in that are so small that you seem to need tweezers to actually look at them. So what is it that you've got here?
One of the main reasons for being interested in kinetic inductance detectors at all is they're very simple devices. You can attach many of the devices to the same piece of readout equipment, which is quite rare in superconducting detectors. Often you need a single readout piece of equipment per detector. If you want to take a large image with high resolution, you need hundreds or thousands of pixels, or even tens of thousands of pixels. Now that's tens of thousands of devices. If each of those devices has their own piece of readout line, their own piece of readout equipment, then the wiring, simply the wiring by itself, becomes an unmanageable task. Now, there are lots of different ways of getting around this, but kids originally gathered interest because you can attach many of them to the same piece of readout equipment and the same readout line. So technically, it should be very easy to make large arrays of these devices. And the reason that my devices require tweezers is kids are very small. They are on the order of millimeters, so even a very large array of them is going to be very small. And second, of course, this is only a test device, so this doesn't have hundreds of thousands of kids. This, in fact, only has 10 kids. So it's only about 8 millimeters long and 3 millimeters wide.
Well, it looks like a piece of sort of perfectly reflective glass, about a quarter the size of a postage stamp. So that has got multiple receivers that can detect radiation from the birth of the universe.
Exactly, yes.
That's quite astounding, really. How does that actually work to pick up that radiation?
With a telescope, you'll have the aperture, which actually sees the sky, and then you'll have perhaps a series of lenses which will take the light that is collected by the telescope and focus it on one point, called your focal plane. Now, at that point, that's where you put your detectors. The kids themselves don't actually absorb light particularly well. You have to attach them to an antenna or an absorber, depending on which wavelength of light you want to look at. And that absorbs the light and transmits it into the kid itself. Now, the kid itself is a really simple device. It's called a microwave resonator. It acts a bit like a notch filter. So if you look at it over a range of frequencies, then what you'll see is an almost flat, perfect transmission from the input to your output, except at one particular frequency called the resonant frequency of the device. Now, at this frequency, all of the energy that you put in to what we call the probe signal goes into the device, gets reflected back, and never comes to the output. So when you actually want to read out from a kid array, what you do is you have a series of devices with different resonant frequencies, so that your transmission across the entire range almost looks like zero. But then if light hits one of your detectors, its electromagnetic properties change, and all of a sudden its transmission at that resonant frequency goes from zero to very high. And that's how you know that you've detected something. And how much the transmission changes by and over what kind of time scale, that gives you information about how much energy the light had.
Sarah Thompson, who's completing her PhD at the Cavendish Laboratory at Cambridge University. Back now to Kirsten Gottschalk from the MRO and our own Dominic Ford, discussing how the two different precursor instruments currently work on the site.
The two precursor telescopes already at Murchison demonstrate two ways that radio astronomers can detect radio waves. On the outside, at least, the white dishes of ASKA look much more like the traditional image of a radio telescope. For high-frequency radio waves, dishes remain the preferred option, as receivers are expensive, and it makes sense to use large dishes to focus the radio waves onto a small number of detectors. But receivers for low-frequency radio waves are cheap. Rather than building huge and unwieldy metal structures to focus radio waves onto a small number of detectors, it makes sense to have many more smaller antennas. This is especially true in a remote location like Murchison, where keeping large moving structures in good repair is costly. The MWA takes this idea to the extreme, having over 2,000 tiny antennas called dipoles, each of which has no moving parts at all.
After our fabulous morning at ASCAP this morning, we're now at the Murchison Widefield Array side of the site. We've had a bit of lunch and some cake, and we've now headed out along the trench lines of the MWA to the core. The configuration of the Murchison Widefield Array is quite similar to other radio telescopes in that you have a dense core with lots of antennas, and then slowly as you get further and further away from the core, the telescope gets more and more spread apart and the antennas are further apart. So at the moment we're in the core of the Murchison Widefield Array. It's about 500 metres away from the MWA office, and radiating out from that office are what we call trench lines. The holes were dug in the ground to run cables along, then filled in, so they look very much like roads. And there's 7 of them radiating out I turn around in every direction. There's just little MWA dipoles as far as you can see almost. And they're clumped into groups of 16, in squares of 16 that we call tiles. One direction I can see about 30 tiles. They're all clumped together. And then the rest of the MWA spreads further and further out, up to about 2 kilometres from the centre. And we've got 128 tiles total in an area that's about 3 kilometres square. And each of these tiles, I walk up to it, it's got 5 by 5 metres of mesh in a big square, and then the dipoles are clipped onto there, the little antennas, and then they've all got cables running out of them that are hooked into this white box that sits off to the southern end of the tile. And that white box is called a beamformer. One of the special things about the Murchison Wide Field Array is that it doesn't actually have any moving parts. You can't point the telescope by moving a dish and pointing it to a certain section of sky. Instead, you point the dish electronically using a computer. And that's where the beamformer comes in. It forms the beam on the sky. So what happens is radio waves are coming in to the telescope, and each of the antennas is obviously at a different spot on the ground, so the radio waves will come into each of the antennas at a different time. And then all of the information is sent through to the beamformer, and the beamformer is told by the astronomer who wants to use the telescope where in the sky you want to look. And what it does is it adds a delay to each of the signals to combine the signals in such a way that you end up looking at the right spot of sky.
Each of the MWA's antennas receives radio waves from all over the sky. But the telescope's control software can choose which direction to look in by introducing small delays into the signals from some of the tiles. Radio waves from the east will arrive at the easternmost tiles first, before sweeping westward across the array at the speed of light. When it's completed, the SKA will produce a colossal amount of data. Since the aperture arrays will comprise of so many small antennas, each retaining their own separate signals, which will have to be added together, the total amount of data flowing into the control computers will be measured in thousands of terabytes per second. This poses serious challenges for the engineers. It means that the site is littered with buried optical fibres, and it's quite impossible to carry all of the data that's flowing through them back to Perth. Instead, much of the computing power behind the SKA will need to be on site, within a few hundred metres of the antennas themselves. The whole point of locating the SKA in the desert was to get away from the radio hum that electronic devices produce. The engineers need to make sure that any radio waves that the computers produce are kept away from the antennas.
The sky has still got hints of blue, but it's mostly got grey cloud cover. We're expecting a little bit of rain tonight. Of course, all of the telescopes are waterproof. But not just that, they're also radio frequency proof, because there's no point coming all the way out here and then building a big power station to power your telescope and building your receivers and your electronics that control the telescope, because they will then produce radio waves. So everything in the MRO is shielded within an inch of its life practically to make sure that it doesn't produce any radio waves that could interfere with the telescopes. This is particularly important for telescopes like ASCAP and the MWA because they are designed to be very, very sensitive. The MWA is designed to pick up some of the oldest signals in the universe, which will be extremely weak. So any kind of signal that's man-made and Earth-based will drown those signals out. So we have things like the CSIRO control building that has 2 massive airlocks to get into it, and they're not to prevent air coming out, but instead to prevent radio frequency interference. And I really like actually how they tested the building and made sure it was radio frequency tight. So they had a big signal generator inside the building, and then we're walking around with detectors and saying, okay, this weld needs a little bit more welding on it because it's letting some out, and then basically made sure the building was completely tight and nothing could get out. And the same has been done to all of the equipment over at the MWA as well. So we have these lovely white boxes sitting on the trench lines. They're called receivers. There's 16 of them. 8 tiles connect up to each of these receivers, and they basically look like kind of a white box with a fridge in it and then a whole lot of electronics, and those electronics produce a lot of radio frequency interference, so the white box itself shields them really, really strongly to make sure that the tiles are picking up nothing but signals from space.
The MWA and ASCAP are being used to test the new types of radio receivers that the SKA will use. Placing them on a site which is very close to where the SKA will be built also tests whether that site is as good in practice as it looks on paper. I have to say the first results that I've seen from both the Australian and South African sites are incredibly impressive. In the absence of mobile phones and television transmitters, these are sites where the background noise becomes significantly worse whenever communication satellites are overhead.
We've just left Bulati, hitting the road. It's about 7:45 in the morning. We're ready for our 8.5-hour journey home on the dirt and then the tarmac. We're looking forward to getting back to Perth, but we're sad to be leaving the Murchison.
Thanks to Kerstin Gottschalk from the International Centre for Radio Astronomy Research, and also to CSIRO for allowing us to record on the site, and Curtin University, who manage the MWA.
And now, with Question of the Week, Hannah Critchlow investigates a hot topic for comets.
This week we cast our eyes to the sky since Jane wrote in with this.
How long does it take for a comet to completely melt away from repeated exposure to the sun? Will there come a time when all the comets are gone from the solar system?
So, do comets melt? And if so, could we ever become cometless? With the answer...
Hi, my name is Katrin Roos. I'm an astrophysicist at Lund University in Sweden. So comets are actually large clumps of ice and rock that were left over when the planets were formed. We can think of them as huge, dirty snowballs orbiting the sun. And being snowballs means that they can melt, and they also actually do melt. Every time a comet passes close to the sun, part of it sublimates, meaning that the snow and ice turn directly into vapor. And this is the vapor that we can see as one of the tails of the comet. So, since part of the comet sublimates every time it passes the sun, it cannot live forever. For example, we have Halley's Comet, which is quite well known since it passes the sun once every 75 years or so. And this comet will be completely sublimated and disappeared after only 10,000 years, or about 100 rotations around the sun. And this is a typical lifetime for a comet. But still, this does actually not mean that there will come a day when all the comets are gone. And that's because there are huge hidden supplies of comets waiting beyond the orbit of Neptune. That's the Kuiper Belt and the Oort cloud. And these regions continuously replenish the inner solar system with new comets.
Thanks, Katrine. So even though comets, like Halley's Comet, will eventually sublimate and disappear, there is a distant reservoir of dirty snowballs that are sometimes knocked into new orbits, making them into new comets. So we shouldn't come across a cometless solar system anytime soon. Well, with that question melted away and replenished, we bump back down to Earth to pose our next question. Anton from the Ukraine wrote in with this.
Hi, I would like to ask a question about artificial photosynthesis. Does it exist? What kind of challenges do scientists have in this field? And what potential benefit to humanity could it bring? Thanks.
So, could we get humans photosynthesizing like plants to help with food security? Or could we use the power of plants to help develop more efficient solar panels? What do you think about that one? Let us know by posting on our Naked Scientists Facebook page. You can tweet at Naked Scientists. You can email Chris at thenakedscientists.com. Or you can join in the live debate on our forum, which is at nakedscientists.com/forum.
Hannah Critchlow. And that is it for this week. Thank you to our guests, Lee Kaplan, Sarah Thompson and Kerstin Gottschalk. And thank you also to Dominic Ford for joining me. The production this week was by Dominic Ford, Ben Vassler and Kate Lamble. Next week we'll be having a family reunion as we find out a bit more about our very early human ancestor, Australopithecus sediba. We've been to the very cave where it was discovered and spoken to the man who found it. The Naked Scientist comes to you from Cambridge University and it's supported by the Wellcome Trust and the EPSRC. I'm Chris Smith and thank you for listening. Goodbye.